Hi, my name is TJ Masters, and today we're going to cover a topic that tends to freak a lot of people out, and that is the electrical system on your motorcycle. The bike in this video is a 1980 Honda CB750, so the particulars are going to apply to all of the Series 2 models produced between 79 and 83, but I'm going to cover some general concepts in automotive electronics, and my hope is that if you're dealing with a no-start condition, or if you're hitting the starter button and you're hearing a clicking sound, or if your battery's not charging, that by the end of this video, regardless of the bike you're working on, you'll have a better idea of how to diagnose and fix the problem if it is electrical in nature. So I'm going to divide it up into the various subsystems on the bike, which are somewhat unrelated, even though it's important that they all work together. And as always, I'll put the timestamps in the description below, so if you don't care to listen to me pontificate, or if you know the part of the bike that you're having trouble with, you can feel free to skip ahead. But before we get to the bike, I think it's important to talk about DC voltage and the concept of grounding. So let's get started. Now, I'm not an electrical engineer, so this explanation is going to be very basic, but I think it's important to understand some of the concepts at work before we get to troubleshooting on the bike. If you are an engineer or someone with a firmer grasp of electrical systems, feel free to correct anything I have wrong here or add to what I'm saying down in the comments. This is all about free exchange of information and educating each other. So what I have here is a very simple diagram of an electrical circuit. And right off the bat, it's probably important to point out that electricity needs a closed loop in order to work. Electrons will only travel through the circuit if there is a difference in potential to compel them to do so. And that's the function of our battery, with a positive and a negative terminal. On the other side of the circuit is a load. This can be anything that converts electricity into heat energy or kinetic energy. For example, a light bulb or a starter motor. All automobiles and motorcycles operate on a 12-volt direct current system. Some really old cars work on 6 volts, but for all intents and purposes, what this means is that 12 volts is always traveling only in one direction, that's the direct part of direct current, through the system. AC, or alternating current, allows for electricity to flow in positive and negative directions, and that does apply to our bikes, as we'll see later when we talk about the charging system. But for now, consider that everything that needs to run runs on direct current. I'll also just add that we tend to think of electricity as flowing out of the positive terminal, since all of our components are connected to the positive side of the battery. But actually, electrons are negatively charged, meaning they're traveling from the negative side of the battery over to the positive. Anyway, it's common to draw it out this way, but if you want to impress your friends with esoteric knowledge, now you know. For our purposes, we can talk about the circuit as either electrified or not, and it doesn't really matter which way the electrons are going. But there's an important side of all this that is often overlooked when you're troubleshooting, and it's a shame because it's literally half of the overall system, and that's grounding. Physically, the ground side of the circuit is how electrons complete that loop to get back to the other side of the battery. You could do this by running an individual wire from the positive terminal to each component, and then back from the component to the negative terminal, but a more convenient way to do this is just to give everything a shared channel back to the battery, and that's the ground. Automobiles are conveniently made out of metal, which conducts electricity, so the ground path is usually through the frame and the engine. You may have noticed that your battery has a short, thick wire from the negative terminal straight to the frame of the bike. This is not a dead end. Each of your electrical components are also connected to a ground wire in the wiring harness, which is green, at least in Honda's system, and that also connects to the frame, sometimes in multiple places on the bike. And so the frame becomes like a giant connector between the negative wire, or the negative side off of your battery, and the ground wire in the wiring harness. And that's what provides the closed loop that allows for the circuit to be electrified. A lot of electrical so-called gremlins are caused by bad grounds. If the ground connection is not secure, you can get flickering lights, poor ignition,
any number of problems that are caused by the electrical circuit momentarily breaking open and being closed again. Maybe this is happening because the bike is vibrating. If you're restoring a bike or you're powder coating your frame, you absolutely need to make sure that you sand off the coating where the negative cable attaches from the battery in order to ensure that you have solid metal on metal contact. Like I said, it's an entire 50% of the overall circuit, and electricity only works when the circuit is closed.
Here's something interesting that I learned just the other day. If electrons are using the frame of your bike to travel back to the battery, and so it can be said that your bike is electrified, how come we don't get shocked when we touch it? Well, there's a few different reasons, as it turns out. One is that your skin is a very poor conductor of electricity, and 12 volts is just not that much. Think about bridging the terminals on a 9-volt battery with the tip of your finger. Nothing happens. If you bridge those terminals with your tongue, the water on your saliva acts as a conductor, and you get a very mild shock. But the truth is, our skin is pretty resistant, and we're just not dealing with that much voltage. The other reason is that when you touch the frame of the bike, your body and the bike share the same electrical potential. Electrons are always going to take the path of least resistance to get back to the battery, which is just physics. So there's nothing in your body to compel them on their journey to leave the bike, go through you, and go back to the bike on their way to the battery. They're just not going to do it. It's faster and shorter for them to go straight there through the frame. Again, physics. Pretty cool. So, make sure you have a meter, and let's get to the systems on this bike.
I want to start with the battery and the charging system. The battery is implicated in all of the bike's electrical systems, but the charging system is somewhat closed off from everything else. It's got a relatively few number of components, and so it's more simple in that regard, and I think it makes sense to start there. Let's talk about the battery. I'm using a Batt MBTX14AU. Motorcycle batteries are frustrating. They're hard to research. And many times for a bike of this age, the recommended OEM replacement is either unavailable or it's an older style of lead acid battery that you have to keep topped off with electrolytes. This is an AGM style battery. It's got a gel inside of it. So it's somewhat more modern, but it's not the super slim lithium batteries you may have seen on the cafe racers or whatnot. And it's hard to recommend a battery. I've gotten bad ones from this brand before. Sometimes that depends on the date of manufacture, how long they've been sitting on the shelf waiting to be bought. And it's somewhat unfortunate that buying a motorcycle battery feels like somewhat of a risk. Anyway, I will say that this battery or a similar AGM style produced by Bike Master, for example, is another brand. That's going to be closest to the OEM specs for this bike. I can't recommend the lithium style batteries unless you're doing a greater overhaul of the charging system. I think they have different needs in that regard, but I can't speak to that because I'm not an expert. In any case, the way to test the battery while the bike is off is to set your meter to the direct current setting, which is represented by a V with a line and 3 dots next to it. And since we're working with a 12-volt system, we expect to read somewhere around 12 volts from this battery. And the different options that you have here on the meter represent different scales with a maximum value here. So since we're only looking for 12-ish volts, I've got it set on 20. And all you got to do is take the red probe to the positive terminal and the black probe to the negative terminal. And we get 12.58, making sure you're pressing hard and making a good electrical connection here because it's all about physical contact. And I haven't run this bike in about 3 weeks, so the battery's just been sitting here and it's holding a charge at 12.5 volts, which means it's probably good. When we talk about the starting system, we'll see that just because the battery displays the correct charge does not necessarily mean that it's operating well under load. We'll get to that a little bit later after we look at the charging system. We're looking at the right side of the bike here with the side cover off, and the charging system comprises the rotor, which is a giant spinning magnet, basically, the stator, which is a winding of coils that is able to generate AC electricity from the magnetic field emitting from the rotor. The regulator rectifier, which converts the alternating current to direct current, and the battery. Now, the regulator and rectifier on many old bikes are two separate components, but on modern vehicles and by way of upgrading, you can get them in a single unit for about $100. I'm not going to spend any time on this video troubleshooting 40-year-old regulators. When you get a new to you old bike, replacing the battery with a brand new one is a necessary start in bringing it up to a well-running standard. And if you're going to spend money on a new battery, you should also spend money on making sure your charging system is not going to destroy it. So from here on out, I'm going to assume that you have an upgraded regulator rectifier. You can upgrade the stator to get a higher output of AC, but by and large, these two components of your charging system are probably okay. Nevertheless, I'm going to show you how to use the meter to make sure that the stator doesn't have any bad windings. The stator connects to the regulator rectifier through this connector on the right-hand side of the bike next to the battery. The stator and the rotor work together to produce an electromagnetic field, which is converted to alternating current and sent to the regulator rectifier through this connector to be converted into DC current that can charge the battery. I've gone ahead and set my meter to the ohms setting and put it on the lowest one. Ohms are a measure of electrical resistance, and you can use this setting on your meter to check continuity. Continuity is an important concept. It describes an electrical pathway from one point to another. There are going to be times when you're troubleshooting and you're going to need to put one probe on one end of a wire, the other probe on the other end of the wire, and make sure that current can flow properly. In other words, that the cable isn't chopped or shredded somewhere or touching the ground where it's not supposed to. When your two probes complete a circuit, the meter will beep at you and show you the resistance present in that circuit. In this case, the reading that we're getting is actually the meter's own internal resistance of 1 ohm, and that's going to be important in a minute. Now we're going to test the stator in two ways. First, we need to make sure that there is no continuity between any of the stator wires and the bike's ground. Remember, the bike's ground is operating on a DC system. Stator is producing AC, and if it's grounded out, it's not going to work at all. So the way to do that is to insert one probe at a time, to one wire at a time, and put the other probe anywhere on the bike's ground. We've got a convenient one right here, the negative pole of the battery. And we get no continuity. Check the next one. No continuity. By the way, when you're checking continuity, it doesn't matter where you put the black probe and where you put the red probe. You're just completing a circuit. Electricity doesn't see colors. And we'll check the other two wires in this bracket, the white wire and the black wire. No continuity. No continuity to ground. So the stator and the rotor require electrical power in order to generate this electromagnetic field, and that comes from this black and white wire here in this bracket that's also running from the regulator rectifier. If it's grounded anywhere, the circuit is disrupted and it just won't work. It won't generate any electricity. The next thing to check is that there's continuity between the three windings in the stator, as represented by the yellow wires. These windings are connected to each other. They're wound together up inside that stator, and we expect to see a small amount of resistance between any of the two pairs. And I'm talking less than 1 ohm would be a good specification. Now that the meter has its own internal resistance, as we saw, of 1 ohm, so when we're taking this test, we want to make sure that we subtract the meter's internal resistance from our reading in order to get an accurate reading. And so the way to do this is just to do one pair at a time. So here's the first yellow wire and the second yellow wire. There is continuity, and we get a reading of 1.5 minus the meter's internal reading of 1 gives us 0.4, 0.5. We'll do the next pair. Same thing. And the last pair, wires 2 and 3. There it is. So subtracting that internal resistance, we get a very small amount of electrical resistance from winding to winding, and that means that the stator is good. And what I mean by good is that it's wired correctly. What this doesn't tell us is how well it's charging the bike. I have the gas tank off this bike for the video, so I'm not going to be able to show you how to meter it while the bike is running, but you can check it in two spots. You can get the bike running and meter the battery like we did earlier. And at the battery, you would expect to see between 13.5 and 14.5 volts. Anything less, and the battery is pretty much actively draining while the bike is running. Anything more, and you've probably got an issue with your regulator rectifier, and it's allowing more current through than it's supposed to be. You can also disconnect this connector while the bike is running. It'll just be running off of battery power at that point, and measure the alternating current, not continuity, but alternating current. That's this setting on your meter, by the way, the V with the wave, between the three windings. And you'll probably get something like 15 or 18 volts at idle. The charging systems on these bikes are extremely weak without that high output stator upgrade. But what you're going to want to do is rev up the bike while you're metering it and look for at least 50 volts AC coming from the meter. Again, this is alternating current that is produced by the stator and the rotor, and it's converted into 12 volts DC current by the regulator rectifier. Moving on to the starting system, and since I'm trying to be as comprehensive as possible, I think it's worth mentioning that you should find a wiring diagram for your bike. This should only be a quick Google search away. You can save it to your computer, get familiar with it. I know that it looks like a total mess at first, but it's really just about tracing the lines which represent wires in the wiring harness. And I'm going to be referencing this diagram, specifically the colors of the wires, for the rest of the video. And I'll try to show you exactly on the diagram what I'm talking about in the physical world when it's applicable. The starting system is also pretty simple and comprises the battery, the starter solenoid, and the starter motor. Also implicated in this particular bike is the starter button on the right handlebar switch, and a switch that is integrated into the clutch lever. This is not a switch in the sense that it's something you flip, but as you'll see in a moment, it plays a very important part in completing the DC loop through the ground of the bike to power the solenoid. Some newer bikes also have kickstand switches that won't allow you to start the bike unless the kickstand is up. This bike does not. Let's talk about solenoids. That's what we're looking at right here. This is an aftermarket solenoid. I paid about $10 for it. If you want to get a Honda brand replacement solenoid, you're looking at $50. Always, in general, you should try to replace parts with OEM parts when necessary, but the truth in this case is that solenoids are pretty battle-tested technology. As we'll see in a moment, they're quite simple devices, and so aftermarket is not really an issue here. The solenoid on this bike is the first thing that the positive side of the battery hits. You can see this short jumper cable is running from the positive terminal of the battery to this pole on the solenoid. And it's doing two things. The solenoid is responsible for transferring power to the starter motor when the starter button is pressed. And it's also kind of acting like a gateway from the battery to the rest of the bike's electrical components. You can see here that it's holding a 30 amp fuse, which protects the bike. And that fuse is connected via this red wire to the ignition switch. I know both of these wires look red. This one has a stripe on it. And the red and white wire to the regulator. And so these are kind of, you think of the power as coming in from the battery here, and it's fused, and then it splits out in two directions. And what that's doing is, on the red side, is protecting the rest of the bike's components, the fuses, and on the white side, red and white side, is protecting the regulator, or probably more accurately, protecting the battery. So if you were to hook up the wrong type of battery, maybe anything other than a 12 volt DC, this fuse would probably blow to protect the rest of the bike, which is accessed through the red wire. And likewise, if the regulator had failed and it was not converting the AC electricity correctly, that would be traveling through this red and white wire, and it would probably cause the fuse to blow, which would protect the battery, as well as the other components of the bike. Take a quick glance at the wiring diagram and you'll see that this red wire that is running to the ignition switch, when it's switched on, it makes a connection to the black wire in the wiring harness. Let me just take a minute here and emphasize something. Whether or not the bike is running, when the ignition is turned on, the black wire is connected to the red wire via the ignition switch, that's where your key goes in, is connected to the fuse, is connected to the battery, and is always carrying 12 volts. Almost everything on the bike, from the turn signals to the ignition coils, taps into this black wire to get 12 volts, and then taps into the ground in order to complete the loop that we talked about earlier. The black wire runs to the fuse box in the handlebars, and from there it breaks out to the various systems. Again, still a black wire, but it breaks out in the fuse box, and in this way it kind of distributes the potential for failure. So if the fuse for your headlight circuit blows, there are still wires distributing power to the turn signals, to the ignition circuit, whatever. Okay, back to the solenoid. The solenoid has two poles on top. One is connected directly to the battery, as we mentioned, and that means that if we were to use our meter and put the positive end on this pole and put the negative end on the battery, negative, it should read exactly the same as the battery. There's literally nothing blocking this connection. It's directly to the battery through that short little jumper. So the key is not even in the ignition right now, and we're making a little circuit here. We've just extended our concept of the circuit over to the solenoid. The other pole runs to the starter motor, and under normal conditions, there is not a connection between these two. That's what the solenoid's job is. So watch what happens if I move the meter, if I move the positive end over to the motor side. Nothing happens. It's because they're not connected. The solenoid's main job is to make a connection between these two poles when the starter button is pressed. The way that it does this is through electromagnetism. Let's look at the wiring diagram for a drawing. The solenoid has a coil of wire inside. And you might remember from middle school science, when a coiled wire is electrified, it creates a magnetic field. Inside of that coil is a tiny little cylinder made out of magnetic material. I don't know what it is. Maybe it's steel or something. And when the coil becomes electrified, the magnetism pushes that cylinder to the top of the solenoid and it bridges the two poles. So let's look at this in practice. I've disconnected the starter motor from the motor pole where the probe is because I don't want it to be spinning here. But look what happens when I turn the ignition on and I press the starter button. The solenoid clicks and voltage passes through. And there I am letting go of the button. Press the button again and release. So under the right conditions, as long as the button is pressed, then electricity is allowed to pass between the two poles. So if you're dealing with a no-start situation, you can measure the voltage across your solenoid like we just did here to make sure it's working correctly. If you hit the starter button and you hear that click, that's the sound of the cylinder inside zooming up to the top of the solenoid and bridging the poles. It's literally, it slams against the plate on the inside, and that's that clicking sound. In other words, if you get a click, then your solenoid is probably not the cause of the problem. If you press the button and you don't hear a click, it could be the solenoid, it could be something else. At this point, what you might try to do is bridge the two poles physically with a screwdriver, just to see if you can get power to pass through to the motor and get the motor to spin, the starter motor. How does this coil become electrified inside? Well, the starter button at the handlebar makes a connection between the black 12-volt wire in the wiring harness and this red and yellow wire. So when you press the starter button, 12 volts is able to travel through the red and yellow wire to the coil in the solenoid, but that's only half the equation. Remember, it still has to be connected to the ground. Well, where is the ground? It's this green and red wire here. I know the stripes are hard to see. There's a red stripe on that wire. This green and red wire runs up to the switch in the clutch lever, and it makes a connection to the ground when the clutch lever is pulled. In other words, the solenoid cannot become electrified until two conditions are met. Both the clutch lever has to be pulled in and the starter button has to be pressed. And more widely, of course, the ignition has to be turned on so that 12 volts is running from the battery to the black wire. Is it starting to come together? Boy, I hope so. So let's reconnect the starter motor to the motor side of the solenoid. That's this thick gauge cable that runs down alongside the bike underneath and to the starter motor. Now you want to be somewhat careful here because if you bridge the gap between these two poles, you are getting out of the switched safety side of the solenoid. You're just literally making a direct connection. So, and that does not have to do anything with the ignition switch since it's running straight to the battery. So you can bridge your starter solenoid without actually having the ignition on. So just be careful when you're wrenching next to these two poles if you're connected to the battery. If you're not connected to the battery, obviously, no big deal. Now, if we turn the ignition on and press the button, I want to come back to this angle just briefly and talk about the battery again for a moment with regard to starting. The starter motor is probably the most battery intensive part of the bike. It pulls very hard on the battery. Nevertheless, you should not see an appreciable drop in voltage from the battery when you're cranking the motor over. I kind of alluded to this earlier, but one way that a battery can be bad is that it can show the correct voltage under a no-load situation, but then when you go to crank the starter, it'll drop to 6 volts, 5 volts, 7 volts. I want to show you what a good battery should drop to when you crank the starter. So you can see we only dropped about 2 volts, 2.5 volts. So if you're dealing with a no start condition and your solenoid is clicking, do not rule out the possibility of a bad battery, even if it reads correctly. As you may or may not know, the starter motor lives under this cover on top of the engine, and I'm not going to take the cover off and show you all what it looks like. There are videos out there on how to rebuild your starter motor if you need to. The starter motor on these bikes was not actually manufactured by Honda. They outsourced that. And so you can get rebuild kits for about 20 bucks. It is an electrical motor, so it's got brushes and an armature. And so if you do need to rebuild it, you'll just want to polish up that armature, replace those electrical brushes. But I just did want to point out, for the sake of this video and the concepts we've been discussing, the starter motor is getting its positive side of the circuit from the solenoid, and that's that thick cable that runs down into here. But where does it ground to? It actually grounds to the engine itself through the chassis of the starter motor. That's a part of the starter motor's internal circuit, is its own chassis. So it's bolted directly to the motor, which is bolted to the frame, which is connected to the battery negative through our battery negative cable. And that's your DC loop for the starting circuit. Moving on to ignition. The ignition system comprises, in the direction of energy flow, the pulsars, CDI boxes, also called spark igniters, ignition coils and coil leads, and the spark plugs. There's not a lot to troubleshoot actively here, as it's kind of impossible to do while the bike is running. There's just nowhere to plug your meter in. If you want a closer look at pulsars and how they relate to ignition timing, you can check out the first video I did about scheduled maintenance. But I do want to mention a couple of things. One is that next to the ignition coil bracket, there is a frame ground coming out of the wiring harness. Remember our model from earlier and how important it is to make sure that there is good metal-on-metal contact here. This is the path through which many components complete their DC loop back to the battery. The other thing to point out is that these bikes have notoriously weak spark systems. In fact, if you're having ignition issues and you have gone through most of the troubleshooting but you haven't replaced the coils and the igniters, I recommend that you do so. The igniters, also called CDI boxes for capacitor discharge ignition, tend to go bad, and there's just no way to know. They're sealed up with epoxy. These boxes have capacitors inside. A capacitor is a very basic electrical component that is capable of storing and releasing a charge, kind of like a battery, except that capacitors can store huge amounts of electricity, and they discharge it all instantaneously. These boxes, as well as the windings in the ignition coils, are part of how the relatively weak 12 volts in the bike's electrical system gets supercharged so that the spark plugs can produce a strong spark. Just by way of demonstration, the connections made here on the left side of the bike represent a pretty crucial junction. The bottom bracket is the wires from the pulsars as well as the neutral switch. The second from the bottom is connected to as part of the charging system and is connected to the regulator and rectifier. It's where the regulator and rectifier integrates into the main wiring harness. And the top two brackets are for the CDI boxes, or spark igniters, which are both receiving power from the pulsars, and they're also discharging power toward the coils. Let's talk about this ignition kill switch for just a second. The components in your ignition chain, namely the coils and the CDI boxes, need a constant source of 12-volt power in order to do their thing. Remember that 12-volt power comes from the black wire in the wiring harness. When the ignition kill switch is in the run position, it's making a connection between the black 12-volt rail and it's passing it through a black and white wire to the coils in the CDI boxes. When you flip the kill switch to the off position, that connection is broken. The coils in the CDI boxes do not get 12 volts, and the bike will not run. You'll still be able to crank it. You'll still be able to see other circuits like the headlights and the turn signals, but the ignition circuit itself will not be able to run. The other thing that lives on this side of the bike is the turn signal relay. If you're having trouble with your turn signals, you might want to look into the relay. This is a mechanical relay that works using conventional incandescent bulbs. I don't have LED bulbs on this bike. That is one way to get around potential electrical problems, just to upgrade to LED, which use much less electricity and are more reliable. When I say reliable, what I mean is that this is actually a mechanical device. There is a little thin piece of metal on the inside of this relay, and when power is applied to the turn signal circuit, that piece of metal flexes and flips, and that's what actually creates the clicking sound for your turn signals. It's the same thing in the car as well. So if you're having trouble with your turn signals, look into your mechanical relay. This thing works based on overall resistance in the circuit. Basically, it's looking for 6 light bulbs: front left turn signal, front right turn signal, rear left turn signal, rear right turn signal, the signal indicator on the dash left, and the signal indicator on the dash right. And so this mechanical action of the relay relies on a certain amount of resistance which is provided by those 6 bulbs cumulatively. If any one of those bulbs is bad or burnt out, the resistance will be different and it will cause this thing to flash at a different rate. That's why when you have a bad bulb on a car, it ticks faster. Most everything else in the bike connects up here in the headlight bucket. And fortunately for us, Honda had entered an era of manufacturing where they were using block connectors. And so each one of these connectors kind of has its own size and slot inside the bucket. And so they're pretty easy to figure out which one goes which. There are still a few bullet connectors up here. If you don't know what I mean when I say bullet connectors, consider yourself lucky. The older bikes, like that 70 CL350 behind me, have nothing but bullet connectors, and they can be kind of a pain to maintain or keep connected. In any case, I'm not going to go over each and every connection inside the headlight bucket. You have a wiring diagram now, so you can follow the signal path from the horn, from the lights, from the headlight, for example. You can see on the wiring diagram where things like brake switches make connections between the 12-volt black wire and whatever component they are trying to power, whether it's the front brake switch or the rear brake switch, what have you. For the most part, that about does it when it comes to electricity. It's not quite as hairy as people think it is. It's really about making good, strong connections and just making sure that everything is in its right place. So, if you have any questions, throw them down in the comments below. If you have any criticisms or want to explain something a little better than I did, you can also use the comments section below. I will not begrudge anyone a good discussion about information and knowledge. Okay, good luck with your project.